All right, so we are doing today's class will be on magnetic field revision, and we have four essay questions, and let's see how far we can go. All right, fine. All of these are model paper questions. They're not past papers. Right. So let's start. Um, Ion source, place in which ions are produced. So we have an ion source here. Velocity selector consists of uniform electric field density and uniform magnetic field density, and then uniform magnetic flux density, and then there's a region where uniform magnetic field density is okay. It's released to a uniform magnetic field region. Let's see, read and see what this is all about. Figure 1 shows a mass spectrometer which is used to study atomic structure. I think you must have come across this in chemistry in your first units and all. The sample is vaporized by raising its temperature. Ions are produced by bombarding a stream of energetic electrons. These ions will be accelerated and enter a section known as velocity selector. This one. Velocity selector consists of electric and magnetic fields which are perpendicular to each other. The charged particles with particular speed will be selected and allowed to pass through the narrow slit A. These ions then travel through a uniform magnetic flux density. The reflector charges will strike the photographic plate, make fluorescence. So when the deflector charges strike, then they will make this fluorescent. Right, so I think that's enough. Let's move on to the question, physics aspect of it. Right, so I think we can first handle the part A. Assume that positively charged ion with mass m and the charge q travels with speed v undeviated in the velocity selector region. Fine. Undeviated in the velocity selector region. Um, the uniform electric and magnetic fields are directed as shown in figure 2. Copy the figure 2 on your answer sheet and show the electric force and magnetic force, neglect the gravitational effects. So this is, I think this is the charge. If we take this as the charge, it's actually a positively charged ion. So I can mark this as plus q. We'll have a charge here, plus q, and plus q will be attracted towards the negative plate. Therefore it will have an electrostatic force acting vertically downwards. Correct, people? Electrostatic force acting vertically downwards. Sorry. And how do you find the magnetic force, people? Now it is a charge with this is a positive charge. Therefore there will be a current because of that charge, and that current will be in which direction? You can mark the current to be in the same direction as the charge, because for us to apply magnetic Fleming's left hand rule to find the magnetic force, we need to know what is the direction of current. And the direction of motion of positive charge are same. So now you use the left hand rule. Left hand rule means your but this is the direction of current, so this will be the middle finger. Left hand middle finger will be in this direction, and wait, and magnetic field is into the plane, so index finger is into the plane like this. Index finger is into the plane, right? Index finger into the plane, that is magnetic field. And middle finger represents the current, so in this direction the middle finger will be pointed, that representing the direction of current. And when you keep your fingers like that, your thumb should look like this, right? This is the thumb, and thumb, as we all know, represents the direction of magnetic force. Therefore the direction of magnetic force is going to be in the opposite direction, like this, Fm. Okay, right. So I saw a few of you, most of you put your hands up. Okay, so let's give 1 mark each for both, 1 and 1 here. Okay, right. On the above diagram above, draw the parts of ions having the following properties. having same mass, having same positive charge, speed greater than v. Name the path as 1. Mm, path 1 now. Speed. Now, when the speed is high, what's going to happen, people? When the speed is high, what's going to happen? Oh, okay, wait. This is a good question. I mean, we know now to analyze this part. For Roman 2, for Roman 2, we will have to consider the factors which affect the forces. Now, magnetic force depends on BQV. All right, magnetic force depends on BQV, and electrostatic force depends on QE. 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 So, if the mass is same and if the mass is same, same positive charge means q constant, no change in q. Speed greater than v, so speed increases. When speed increases, who will increase, people? When v increases, who will increase? Magnetic force will increase. Magnetic force will increase. Magnetic force will increase. So we have a upward force, increasing upward force, no? An increasing upward force. It's already entering horizontally towards right, so we have now an increasing upward force. Therefore, path 1 is going to look like this. No, I will draw it. Shall I draw it? I will draw it separately, otherwise it will be a little confusing for us, no? This is the charge, and it is attempting to move this way. It's supposed to go this way straight, but now we are making some changes to it. Therefore, it's going to alter the path. Its path is going to be altered. So I don't know whether it will go straight or not. So for the first path is obviously, the force is increasing upwards with time. So there will be a upward. The path will bend upwards like this. This is going to be path 1. Okay, because upward force is increasing. Why is it bending like that? Because listen, initially charge enters horizontally, and upward resultant force increases. Upward resultant force increases. If it was rest and starts, then it will go up, but it is already moving right towards right now, people. Then you're pulling it up. Upward resultant force increases. That's why it bends like that. Done. Roman 2. Having same mass, same speed, and negative charge of magnitude greater than q. Negative charge of magnitude greater than q. Negative charge of magnitude greater than q. Now what's going to happen here? So Roman 2, we'll have to analyze it separately, no? Negative charge. So it is going to have a electrostatic force upwards. Agreed, people? Electrostatic force upwards. And what about the other one? Electrostatic force upwards, and magnetic force will be now downwards, because the direction sign of the charge changes means magnetic force will be downwards now. Hope you all can agree with me on that, because if a negative charged particle tries to go towards right side initially, means the current is in this direction, opposite direction. Correct? Current is in the opposite direction. If the current is in the opposite direction, when you use Fleming's left hand rule, you will be getting the direction for magnetic force in the opposite. But remember, what about the resultant force now? Their mass is same, speed is same, negative charge of magnitude greater than q. Will that create an impact, people? Now Fe, we know Fe is equal to QE. Fe is equal to QE, and Fm is equal to BQV. V and V are going to get cancelled off, no, when you equate them in case. So it's not going to change its path. It's going to continue in the same path, right? It has to continue in the same path. Yeah. The first one, it will bend upwards, because there's going to be a resultant force upwards. Here, the magnitude q. Now it's like this. Let's say earlier q was just q. Now you are double q. Sorry, when you double the value of q, but this will get double. This will also get double. Both of them depend on simple q. Therefore, whatever the change you make for simple q, the change will happen for both electrostatic force and magnetic force. Therefore, the path will remain the same. It will continue to move in the same path. This is going to be path 2. No change. I think this is path 1, right? Path 1. Path 1, path 2. Why path 2 like this? If q is increased, the reason q is increased, both Fe and Fm will increase by same multiple, will increase by same factor, will increase by same multiple or same factor. So there will not be a change in the path. Let's settle to that. Right, so let's express it. Sorry, the 1 point each. They are not asking us to explain, remember, they are not asking us to explain. All they ask us to draw this. So you should draw path 1 and path 2 in this diagram itself, but I've explained them separately a little bit. So 4 marks here, in one for this, one for this. Moving on. And they have told the fact that is it moving undeviated? Yeah, undeviated. This is important. This point is very important. It moves undeviated. Charge q travels with speed v undeviated. That means these two forces are equal to each other. That's why it moves undeviated. Did I have an expression for v in terms of E and B? Now that can be done quickly. How is that? Charge travels undeviated. Charge travels undeviated. That means it is not showing any change in its path. Charge travels undeviated. So what can you say? So upward force should be equal to downward force. Upward force Fm equals Fe. I'll take the first diagram. Fm equals Fe. For both it's the same equation. Fm QV. Fm is going to be QV and Fe is going to be QE. Now where have we done this before? In magnetic field, in a particular section, we do this. We equate the magnetic force and electric force and we get an equation for V. Where is that? It is E over B. Where is that? Exactly, Hall effect. In Hall effect also we use the same thing. In Hall effect, there will be a situation where the electrostatic force and the magnetic force become equal to each other. Alright, so again people, yeah, 1 mark for this whole thing. 1 mark for this whole thing. 1 mark. Right, so we have 1, 2, 3, 4, 5. Right, alright. So this is how this the mark allocation goes and the answers for this square part. Right, then let's move on to the next part. So it is a combination of electric field and magnetic field, and you can't expect only magnetic field concepts in magnetic field questions. They are sometimes, because charges, when charges are involved, they will mix both. Right. Next one will be, and I think we can, I don't know whether yes, but let's see. B and C, I hope the are readable to you. It's readable. It's not readable enough, let me know. Increase the size. Okay, out of curiosity, can I know quickly if you hope the size of the fonts? Okay, manageable, right? Right. Thank you. Now consider a situation. That the positive ions emerging from A enters the deflecting region having uniform magnetic flux density B naught with speed V. Right, so the charge is was emerging from, does it deflecting V? Okay, right. This it's entering now. They're entering this region at speed V. They're entering. What is the path of the ion in this region? The reason. So magnetic field, people stay the right. Magnetic field, they have not given the direction. Have they given the direction? They have not. They have not. So let's. It's just a magnetic field. But anyways, what will happen? Path enters a magnetic field like that. Just a magnetic field. It will be B1. I mean, a charge entering a magnetic field perpendicular to the field. What will happen? The path will be circular path. Circular path. And they are asking us to explain the reason as well. So what's the reason, people? What's the reason? Because centripetal force. Oh no, you'll just say force, no? Magnetic force. Before we say centripetal force, magnetic force acts always. Magnetic force acts always perpendicular to the direction of motion. Perpendicular to the direction of motion. That is what, that's the requirement to the direction. That's a requirement for a circular motion. Direction of motion. All right. Sorry. Moves anti-clockwise. How do you know that it's anti-clockwise? Have they mentioned that? Wait, anti-clockwise. How do you know it's anti-clockwise? Plus sign. Okay. What the charge? Sorry, the direction of magnetic field, is it given? Is it into the plane or out of the plane? Second part only the direction is mentioned. So here you just have to mention what path it is, whether it's into the plane or out of the plane. The motion, subsequent motion of the charged particle will be circular motion. So that's all we have to mention here. Magnetic force is always perpendicular to the direction of motion. No, it's not a necessity for to mention that it's constant. It's not necessary about mentioning constant force. If you just mention that the force is always acting perpendicular to the direction of motion, that's okay, right? All right. Mark the point at which the ion strikes the photographic plate as X. If the magnetic field is directed normal to the paper in the outward direction. Okay, that's very interesting. In the outward direction. So this is the diagram. Roman 2. I'm going to do it here itself because we are supposed to copy this diagram and draw. So let's take this as Roman 2 and outward direction. Where? Outward direction. So I have to mark the magnetic field this way. Outward means circle and a dot. Circle and a dot. That is magnetic. This is the magnetic field. And what is the charge, people? Is it a positive charge or a negative charge? It's a positive charge, no? Because definitely in mass spectrometers, we use positive charges. Electrons are bombarded on atoms, and from atoms, electrons are removed. So, anyways, we are definitely going to get positive charges. So, if you apply Fleming's left-hand rule, what is going to happen? Let's apply Fleming's left-hand rule. This is the direction of magnetic flux density B out of the plane, and if this is a positive charge, like we discussed earlier, positive charge, and that means the direction of current will be same as the direction of motion of positive charge. So the positive charge is going to create a current like this. Left hand rule. There is a force downwards, no, people? Magnetic force downwards. There will be magnetic force downwards. Hope you all can agree with me on this. If you use Fleming's right hand rule, Fleming's left hand rule, sorry. So thumb index, and this direction is the current. I mean middle finger, and this direction this is force, thumb. Okay, I'm getting it downwards. I hope you also got it downwards. Yeah. Okay, so if there's a force acting downwards, what will happen to this? What will happen to this part? In magnetic field theory parts, you must have learned if you pull it downwards, then it will do this circular path, and it will perform a circular motion, and it will eventually hit the photographic what do you call that, photographic plate at x. So this is x. It will perform circular motion. This is the circular path. So this is, if you're wondering how can this hit the photographic plate, this is how it happens. All right. So let's say one, right? One mark for that. 1 mark. Right. So they're expecting you to just mark this x. That's it. So I have written all these things to just explain. Okay. I hope you all know how to use Fleming's left-hand rule. This is Fleming's left-hand rule for your reference. Right. What will be the speed of the ion when it strikes at the point x? What will be the speed of the ion when it strikes vehicle? It will be what? Will there be a change in the speed? It will be v. Remember, we are supposed to ignore the gravity's effects. I think they had mentioned that before in a previous question. So you can't apply mgh and all those things. So mg is out of question, and always the reason v is the answer. That's it. So if you write v, you will get full marks for that question. You're asking for speed, remember, not velocity. Speed doesn't change. One, that's all. No? Are they asking for reason? No, they are not asking for reason. 1 mark for this one. But the reason for that, why is the reason? What's the reason? Why doesn't v change, the magnitude change? Simple answer. Come on. Why doesn't the magnitude of velocity or speed change with time? If it enters at v, it will hit point x at v, same speed. Why is that? That's because uh, no work is done by magnetic force. Since it always acts perpendicular to direction of motion. Perpendicular to direction of motion. If it acts perpendicular to direction of motion, people, there will be no change in magnitude, but direction will change. There will be no work done by that force. So kinetic energy is not going to change. Kinetic energy is going to remain constant. Kinetic energy is not a vector, people. Right. Then next one. If x is the distance of xa, what is xa? Show that x is equal to em over qb naught. Wow. What is a, people? What is a? Yeah, a is the slit in the previous question. A is the slit. So this point is a. Remember, we have given in the diagram already. This point is a. So tell me, what is ax? Tell me another definition for ax. Another definition for ax. That is now if you take that circular path, I'll draw the circular path again. Okay. X by 2. What is x by 2, Hasna? I didn't get you. X yeah, but what is simple x here? Wait. What is simple x? If x is the distance of x from a, x First, let's draw that again because it's a little too congested here. So take Roman 4. Take Roman 4. Let's draw the diagram, rough diagram. Our charge is it's entering at speed v, and whole distance is x, correct? This whole distance is x, people. And yeah, and what is this? The distance I'm marking. Tell me what this distance is. What is this distance? This is the radius, right? This is the radius of the circular path, capital R. Capital R is the radius of the circular path. Okay, so x in fact 2r. X is going to be. So to find x, what we have to do is we have to consider for circular, right? Consider for circular motion. Centripetal force is equal to v squared r. What is the centripetal force here? Centripetal force is the magnetic force, that is equal to mv square r. And for magnetic force, we can what equation? B naught, actually. B naught, is it B naught? B naught. It's B naught. B naught. They have already given B naught here. B naught. Careful. B naught charge Q V. That is the magnetic acting on the in that particular region, equal to M is missing. No, M is the MC. Okay, M B squared over R. So this V and one of this V will get cancelled out. Hence, capital R will be equal to what? Capital R is going to be equal to MV over B naught, MV over B naught Q. But find x, but we know x is equal to what, people? But x is equal to 2r. X is equal to 2r. According to the diagram, x is equal to 2r. So x is finally 2mv over b naught q. Still don't have the answer. Still don't have the answer. What else should I substitute? Remember, we found an equation for v. What v is equal to what? E over b. E is equal to E over b from a. Before here a part. See, a part 3. We derived a equation for that. So finally, x is going to be the equation a to b over e over pb naught. Yes, the equation. So yeah, that's interesting. Use the values we did earlier and get the answer. Okay, right. So if you allocate marks for this one, the 2 marks for this whole thing. 2 marks. Total 2 marks. Getting the equation, this equation 1, and getting this final part 1. Can I know? Sorry, how many of you got this? Give me a second. Good job. It's all about applying the equations you know for magnetic field and combining everything. So these are the answers for B1, 2, and 3, and 4. Now let's focus on part C. Don't know whether we'll be able to complete part C here itself, but let's see. Okay. Sorry, people. two positive ions of an isotope with masses m1 and m2. We know isotopes have same number of protons. They have different number of neutrons, so their masses are different. Atoms of same element with different masses enters into the magnetic field B naught with same speed through A, strike photographic plate at points X and Y such that AX is bigger than AY. What is the mass of the isotope that strike X? Let's strike at X. Okay, good question. Now if you take now if you analyze this part, I think you can check it simple. You can check it. Sorry, we can compare it in a simple manner. It's enters that they are entering from A, and then one of them is striking here, and the other one is striking here. Y, oh no, Y is smaller. No, people, Y is smaller. Sorry, X is larger, Y is small. Two paths. There are two paths. So which path has a smaller radius now? This is A. This point is starting point is A. When you compare like this. So radius of AY is smaller than radius of AX, obviously. And we have derived an equation for radius. Look, radius is equal to mv b over radius is equal to mv over b naught q. Tell me who are the constants here? Radius is equal to mv b naught q. So who are the radius here? Two positive ions, so they both will have the same charge, plus plus. V, yeah, same speed, V is constant. B is also constant. So radius depends on mass. Radius depends on mass. So here you can say radius is proportional to mass. What's the reason? Because B naught, Q, V, all of them are constants. So what is the answer for this question, people? M1 is bigger. Whoever has higher radius should have bigger mass. Then M1 is the answer. Correct? M1 is the answer. So radius of AX, is already, I've written this one. So from this you can say, M1 should be X, should strike X. M1 should strike X. M1 is the answer. And they are not asking us for explanation, no? Just one. So I think we'll give you 1 mark for that. But it's better to know the reason, or sometimes they will ask you to explain. So this is it. Derive an expression for the separation between X and Y. D in terms of E, B, B naught, M1, M2, Q. Wow. Okay, that D, people, this is that D. No, it's too congested. This separation between X and Y is given as D, this simple D. Separation between X and Y, that is this distance D. Okay, so we have to find that equation. So what's the plan? I think we have already derived the equation for X here, X. We have already derived the equation for X. X is the distance between A and X. So if I go to Roman 2, that is Roman 2, simple. X for path, no, if not, I'll get AX, length AX, that is equal to, use this, that is going to be 2m1e over BBQ. So, correct? Yeah, that's it. And what is AY then, people? Ay is going to be equal to 2m2 E over B naught Q. That's all. Then the question is separation between x and y. So simple D is actually equal to Ax you are subtract Ay. Ax you are subtract Ay. X is 2m1E 2m1E over B naught Q minus 2m2E over B naught Q. Since there are a lot of common terms, I think we can take 2E over B naught Q out. Inside the bracket we can put m1 minus m2. Okay, so it looks stare at this at once, it will look a little intimidating, but if you stick to the basics, it's not that we already have derived an equation for Ax, an equation for Ax and Ay, and then it's all about substituting the value carefully, and you will end up in this. All right, anyone who got this one equation for simple D? All right, good. I can see hands going up. Good job. Then we'll move on to part. In an experiment with chlorine sample, it has been observed that the two isotopes chlorine 37, I think this is from O level, A level chemistry first lessons, hope you can remember. Chlorine 37 plus, chlorine 35 plus entered through the slit with 500 meters per second. So that is V is given to us. Masses of chlorine 37 plus and chlorine 35 plus are 6.17 into 10 power minus 26 kilogram and 5.83 into 10 power minus 26 kilogram respectively. So this is M1, this is M2. M1 is bigger than M2 na paper. B naught is 2 microtesla and the charge of the isotope Q is plus 1.6 into 10 power minus 19 coulomb. When you have plus charge, it is the charge of a proton. Find the separation between the points at which these ions strike the photographic plate. Easy. They are asking for D. They are asking us to find D with the values provided to us. So C3, we have already derived an equation D that is equal to 2E over B naught Q. Right. B naught Q. Simple B naught Q, yes, within bracket M1 minus M2. But there is a problem here. Someone is missing. Who is that? They have not given us a quantity. What is that? They have not given us two quantities. What are they? They have not given us E and B. They have not given us E and B. But instead of E over B, we know we can put what? 2V over B naught Q into M1 minus M2. All right. So instead of E over B, we can use this equation. They have given us V, that is the velocity. So here I'll just add that part. What happened here? Because V is equal to E over B. Now it's all about substituting the values. We have a 2 here, 2 into V. V is 500 divided by B naught. Okay, I think I need some extra space to get it done. 2 into 500 over B naught. Look at B naught, it's 2 microtesla. So it's 2 into 10 to the power minus 3 and the charge is the charge of one proton, that is 1.6 into 10 to the power minus 19 coulomb. Inside the bracket we have the masses. M1 is this is going to be M1 because that is the larger mass, and this is going to be M2, right? M2. So M 6.17 into 10 to the power minus 26 kilogram. It's in kilogram, so no need to panic. Minus 5.83 into 10 to the power minus 16 coulomb. Minus 26, sorry, 26 coulomb. Minus 26 kilogram, not coulomb. Fine. Anyone who simplified this paper? 500, some simplification to do, no? If anyone simplified it, let me know. I'm getting 500 into 10 to the power 22 over 1.6 into here 6.17 minus 5.83 is going to be 0.34 into 10 to the power minus 26. Any answers? 1.063 into 10 to the power minus 2. Meters. Is it? Meters. Says 10.65 millimeters. Right. So it's 500 into 34. 170. No? 170 divided. Is it? 100 divided by 1.6. 10 to the power minus 4. So that is 0 point people 0.1063 meters. That's the final answer I'm getting. Anyone else do this? Or is it different? The 10 to the powers. Let me check the answers. There's a decimal place. 1.63. Okay. Amna has got this answer. See, now you have got 0.106. Hasna, what is this? Multiply by 10 to the power minus 3. Yeah, your answer is fine. No? Here, 10.63. Yeah, millimeter. Yes, yes. 10.63 millimeter. Exactly. Okay. So, 3 of us have got the same. What the others? 10.63 millimeters. But they are just asking for distance. So, if you stop here, it's enough. They're not asking for it in any specific unit. And this looks like a reasonable answer. Sorry. Right, so let's stop it there. Is that all? We have another question, another part. Now, do we have another part, or is that it? Mark allocation for that. How many marks have you already used up, people? 1, 2, 3, 4, 5 with the 6. Previous questions, I don't know. For this one, we forgot to allocate marks. I don't know. We'll have to. 2 equations here, 1 and 1 will be too much. I don't know. Here 1. 13 given already, is it? Right, never mind. I kind of lost track of how many marks. Okay, sorry. Here 1 for this, 1 for this. Now how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For part A, how many marks? Okay, never mind. Let's this is the allocation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 here, no? 12 marks here. Part A, anyone? Let's take a screenshot. Okay, never mind, people. Just roughly you can get the marks now. But it's better to know what's the total. I think I missed certain parts. Anyways, never mind. Question number 2. A proton which is initially at rest travels across regions A, B, C respectively. A, B, C respectively. region A, proton accelerates through 320 volt potential difference. So there is a potential difference. Some numbers are marked. These things should not be marked on the diagram, but they are anyways. But right, let's mark them. The potential difference of 320 volt. 320 volt. Sorry, 3200 volt. Yes. Region B. Region B. With uniform magnetic flux of density 1.2 Tesla directed out of the plane. You can see that. So in region B, we have a magnetic flux 1.2 Tesla. I think that is what they written, I think. And uniform electric field perpendicular to the direction of motion of the proton, region C, contains the same magnetic field as in region B, but no electric field, uniform field, and uniform electric field perpendicular to the direction of motion of the okay. So there is an electric field as well. That means I think we are creating an electric field so that it can continue to go straight, no? Right. Okay. Remember, this is the direction of magnetic field out of the plane. That means what's the direction of electric field then? Are they asking for that? I think they are asking for that, right? Let's talk about that later. Right. Roman 1. A Roman 1. With what velocity the proton leaves region A? How are we going to do it? Mass over charge ratio for proton is given. Mass over charge ratio for proton is given. And how are we going to find it, people? Is okay. Proton is starting here at rest, remember? Proton is starting here at rest. So initial speed is 0. And it's accelerating. Therefore, when it comes here, the proton, it will have a velocity v. Asna, you asked something about the second question. What was that? The proton. Let's take the mass of it as m. The charge of it as plus q for the time being. Proton means positively charged. Asna? So if it is a proton which is to be accelerated, this should be a positively charged plate, no? Due to the voltage. This should be a negatively charged plate. That's why proton is getting accelerated like that. Now, there are two ways of finding, for proton, that is kinetic energy gained by proton. Kinetic energy gained by proton. Kinetic energy gained by proton, that is equal to work done by electric field. Work done on proton by electric field. All right. You can't apply equations of motion here. You can't apply equations of motion. If you this is the way you have to do it, because they have not given you. I don't think, because to apply equations of motion you will need the distance. They have not given the distance. No? Work done by electric field on proton. So the work done on electric field by work done by electric field on proton will convert to its increase in kinetic energy. So kinetic energy gained by proton can be taken as half m u square. Become u square. Take it as u square, because sorry, they have already we will use v for this thing, voltage. Half mu squared equal to, what is the equation for work done? People, work done is qv, q delta v, no? Q delta v. Q is the charge, delta v is the potential difference. So u squared is equal to 2q delta v over m. Therefore u is in fact equal to square root of 2q delta v over m. Mass over charge ratio is given to us for proton. That is mass over charge. M over Q is 1 into 10 to the power minus 8. That means Q over M is how much? 1 over 1 into 10 to the power minus 8. That Q over M. So U is equal to square root of 2 into delta V is the voltage, that is 3200, into 1 over 1 into 10 to the power minus 8. Is that clear, everyone? Hope that's clear to everyone. All right, fine. So finally U is going to be equal to here 2 into 32, that is 64. 10 to the power 2 here and 10 to the power minus 8 goes up and becomes 10 to the power 10. So final answer 8 into 10 to the power 5 meters per second. This is how you have to do this question. They have not given you the distance, so you can't use F equal ma and all those equations. This is the only way you have to do this question. The only way you can actually do this question. So 2 marks for this, 1 mark for coming up to this point, figuring out this equation for U, and 1 mark for this. So if you have come up to 8 into 10 power 5, then totally you will get 2 marks. Can I see raise of hands if you got these answers? No? Okay. Right, Roman 2 now. Roman 2. Proton travels in a linear path in region B as shown in the figure above. Linear path means undeviated. Find the magnitude and direction of electric field in region B. Electric field in region B. Now we already have the magnetic field. What is the electric field? So what's the plan, people? Number Roman 2. First of all, let's find out the direction of magnetic force. So what is the direction of magnetic force? Magnetic force, Fm, we'll put Fm. Fm will act in what direction? Will act left hand rule, downwards, no? I'm getting it downwards. Downwards. Will act downwards because if you lose Fleming's left hand rule. If you use Fleming's left hand rule, you'll be getting, see, direction of current is towards this side because proton is moving towards right side. That means the direction of current also should be in that direction. Direction of positive charge and direction of current are same. And wait, the magnetic field is out of the plane like this, no? Magnetic field is out of the plane, so thumb is directed downwards like this. So downwards, that is thumb, the force, and in this direction will be the current, that is index finger. This is not index finger, middle finger. This is the index finger. Right, so it's downwards. If Fm is acting downwards, so whatever the direction of electric force, people, so electrostatic force, but proton travels in straight line. 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 So electrostatic force should be how? Electrostatic force should act upwards. Then only the proton can continue to move in a straight line path. go this way, and the forces. This way. What is it? Upwards. If E should be upwards. Oh, sorry. If E should be upwards, Fm should be downwards. Then what should be the direction of the, sorry, the direction of the electric field, people? This is plus Q now, proton plus Q. So electric field should be from where to where? If you want to create a upward force, electrostatic force, the negative terminal should be up. Negative. And this is positive. Alright. So ultimately the direction of electric field must be where? Upwards, is it? From bottom to top, this way. E. So electric field should be vertically upwards. That is what they're asking. Magnitude also we have to find out. Magnitude also we have to find out. We know for straight line path, we know Fe is equal to Fm. And what is Fe is QE. Fm is BQE. And Q will get cancelled out. What are we supposed to find out? Capital E. Then capital E is going to be equal to VV. Here, capital E is going to be VV. Let's substitute values. E is going to be B now. B is 1.2 Tesla into V. What is the velocity, people? We found it. 8 into 10 to the power 5. 8 into 10 to the power 5. So final answer is going to be equal to 9.6 into 10 to the power 5 Newton per Coulomb, or you can also volt per meter. These two units must be mentioned, and it should be vertically upwards as well. Find the magnitude and direction. The magnitude and direction both expected of us. Good. So you have to show all these things now. Showing these two, 1 mark for this, 1 mark for this, 1 mark for this, and 1 mark for the magnitude. 1 mark for the magnitude. 9.6 into 10 to the power 5. 4 marks total for that question. Correct? Yeah. So this is how that how the marking goes. We have already allocated 1, 2, 3, 4, 5, 6 marks. We have already allocated 6 marks. All right, people. Good question, huh? Next one. Which path the proton would take out of X and Y in region C? Support your choice with proper reasoning through concepts of physics. Okay, Roman 3 now. Let's focus on Roman 3 here. This is A part, Roman 3. Now what is happening here, people? It is entering a region. C is a region, same magnetic field in region, but no electric field. Here, I mentioned region C contains same magnetic field as in region B, but no electric field. So, proton in region C, proton is going to experience only one force. Proton, it is going to attempt to move this way, and the magnetic force is going to act where? Downwards. We have already found it. You no need to waste our time for that. We are going to, sorry, it's going to act downwards. So eventually proton is going to take a path like this. Draw a circular path. Proton is going to take a circular path like this, because there is a magnetic field already created out of the field. Yeah, B. So what is the path? Path is going to be Y. Y is the correct answer. Just 1 mark. No, not 1 mark. You have to show 2 marks. Sorry, 2 marks. You have to show this and this. It will experience a downward force. So it will experience a downward force. Therefore, it's attempting to move to the right. Suddenly, it's pulled downwards. So it will perform circular motion downwards in a downward path. So indicating this and Y are the important points here. Then the fourth part, A Roman 4. We'll do. So we're done with, I will focus on that here. A Roman 4. What is the radius of the curved path the proton travels in region C? That's easy. We have to apply what people centripetal force equation. No? Centripetal force equals mv squared over r. Centripetal force is going to be the magnetic force Fm equals mv squared over r. And instead of Fm, you can put bqv equals mv squared over r. All right, over r. So v is going to get cancelled out. One of the v's. So R is what we are supposed to find out, right? R is going to be equal to just like the previous question, mv over bq. mv over bq. M over q, we know m over q is this. So I will write it this way: m over q multiplied by v over b. So for m over q, you can substitute that value directly, 1 into 10 to the power minus 8, correct? Into v. What is v? 8 into 10 to the power 5. 8 into 10 to the power 5 and divided by magnetic flux, that is 1.2. Magnetic flux is 1.2 Tesla, isn't it? So that should give us an answer. Anyone got an answer for this, people? What is the answer? It is 8,000 over 1.2. 8,000 over 1.2. What is it? Right, 6.67 into 10 to the power minus 3. Hasna says that's the answer. Anyone else who got an answer like that? 6.67 into 10 to the power minus 3. Okay. Amna also has got the same answer. Right, okay. 6.67 into 10 to the power minus 3 meters. Okay, I'll go with that answer. Looks like that. 8 and 12, it's 2 by 0.3, 20 by 3. Yes, that's the answer. That's the answer. So overall, we will be getting 2 marks for this. I mean, writing this part, this equation, and then finally getting this value, 1. Don't forget the units. Units should be there. So overall, we have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marks for this part. Roman, okay, 4. Thank you. Okay. Now part B, part of the second question. From electric field intensity of 100 Newton per Coulomb exists between two vertical metal plates positioned at 1 meter separation as shown here. A particle of mass 1 into 10 to the minus 15 grams and a charge of plus 1.6 into 10 to the minus 19 Coulomb is released from the top positively charged metal plate at point X. So this is where that point is released. Charge is released. Copy the diagram onto your RS script and mark the force acting on the particle. So draw its path. Now you had to be a little careful. First, let's find weight. Weight is going to act. Obviously, weight is going to act, and we all know weight is equal to mg. And for m, what should I substitute? This value: 1 into 10 to the power minus 15 into 10 to the power minus 3 to convert into kilograms into 10. Okay, this is in grams. So this should be 1 into 10 to the power minus 18 kilograms. Remember that. So I'm getting the answer in the form of 1 into 10 to the power minus 17 Newton. That is the weight, people. Weight. And then let's try to find out the electrostatic force. You find out the electrostatic force. The equation is QE. So Q is 1.6 into 10 to the power minus 19, like a proton. is it a proton or a charge? A charge, okay, particle. Into E is given as 100. So what's the value there? The value there is 1.6 into 10 to the power minus 17 Newton. So if you compare these two values, they both are in the same range, 10 to the power minus 17, 10 to the power minus 17. So you cannot ignore any of them. So weight should be taken into consideration. It will be acting downwards, and the electrostatic force will be acting in this direction, Fe. So it is like there's going to be resultant force acting in this direction. So what is going to happen to this path? The path is going to move in a projectile path. It's going to take a projectile path like this. It's going to take a projectile path like this because it attempts to go to sideways and downwards as well. So it will be like this. Okay. So mark allocation, we have already used up how many marks? 10, right? 10. So put we'll go with 1 mark each. One for this path, half, half and half. Half. This is half. Right? Fine. We don't have. I just calculated this to show you that they should be considered. Usually we ignore the effect of weight for such small masses, but here we can't. And what are the accelerations the particles experience horizontally and vertically? Horizontally and vertically. So let's find them out quickly. This is Roman 2. Roman 2. First of all, let's apply vertically F equal ma. There's only one vertical force, that is mg equals ma vertical. So m and m will get cancelled out. A vertical is equal to g, that is 10 ms minus 2. Simple. Horizontally, if you apply F equal ma, right, Hasna has got 16 ms minus 2. What about the others? Horizontally, if you apply F is equal to ma, there's only one force acting, that is the electrostatic force equals ma, and electrostatic force is QE equals ma horizontal h. So horizontal acceleration is going to be equal to QE over m. Q is 1.6 into 10 to the power minus 19 into E is 100 over m. Mass is 1 into 10 to the power minus 18. Don't forget, it should be converted to kilograms. So 16, I'm getting 16 ms minus 2. Good. 16 is the answer. Simple, people. Right. That 1 mark each. 1 mark each. One for this. One for this. And Roman 3. What is Roman 3? What is the time interval the particle would take to reach the negatively charged metal plate? Ah, nice. Okay. Horizontal. It's starting from rest. Is it? Is it released? Released. So it is released. So its initial velocity is 0. The particle's initial velocity is 0, and it has acceleration in both the directions. That's a very interesting question. Unlike the projectile motion questions, so its initial velocity, I mean, horizontally and vertically both are 0. Remember, initial velocity horizontally it is 0, vertically also it is 0. But I think we don't have to make it too complicated. I think we can finish it off like this. I mean, if you apply the equation horizontally, it's done and dusted, I think, no, people? What time interval they're asking, no? So it's going to eventually reach here after following a path like this, and we know the horizontal displacement. Horizontal displacement is known. How much is that? 1 meter. S is equal to 1 meter. We know the horizontal acceleration, that is 16, right? 16 ms minus 2. ms minus 2, and horizontal initial velocity is 0. So time here will take it as 0, and time here will take it as t. Then you can apply what equation? Will S equal ut plus half at squared horizontally? S is 1, 0 plus half into 16 into t squared. That's it. Yeah. So I'm getting t squared. T squared is 1 over 8 for me. 1 over 8. T is equal to square root of 1 over 8. That is 1 over 2 root 2. No? That is 1 over, for root 2 we'll put 1.41. 1.41. 1.41 damn 2.82. 2.82. So what's time? Time, anyone found this value? 1 point. No, Hasna, I'm not getting that answer. It should be less than 1. No? It should be 0 point something. Anyone else who got this? Wait. I think we could have done it better. Oh, I think I may have screwed it up. Wait. There's a simpler way of doing this. People, sorry. I think I made a mess here. I could have done it this way. I could have multiplied up and down by root 2, so it's root 2 over 4. Root 2 over 2 into root 4. So that's easier. 1.414 divided by 4. This is easier. So time is equal to 0 0.3 5 3 seconds. This is what I'm getting. Anyone else who came across some an answer like this? Oh yeah, Hasna has made a calculation. Anyone else? This is a very simple question, people. Very simple question. So 1, 2, 3, and I think we can settle for 1 here as well. Yep, 1. 15 marks in total for this question. 15 marks. 1, 2, 3, 4, 5. Earlier, I think for part 8 was 10 marks total. That's it. Projectile motion, but not. It has a horizontal acceleration as well. Horizontal initial velocity is 0. So just mark the vectors and do it. They might ask the vertical height and all. Then you can apply the equation vertically and get the answer. It's right. But they are not bothered about that. No, they're just asking for time taken. All right, so we are going to start the question from magnetic field. We are going to focus on electromagnetic induction. All this time it was about force acting charge, mainly forces acting on charge. So this time let's focus on electromagnetic induction. State Faraday's law of electromagnetic induction in words, and after that they are asking to state Lenz's law. Lenz's law of electromagnetic induction in words. So first one, row 1, Faraday's law. Faraday's law states electromagnetic induction induced electromotive force induced electromotive force induced due to electromagnetic induction is directly proportional to is directly proportional to is directly proportional to rate of change of magnetic flux. Rate of change of magnetic. I mean, so if you haven't these things, make an opportunity for you to revise the concepts of magnetic field. Rate of change of magnetic flux. Rate of change of magnetic flux. Rate of change of magnetic flux. Yeah. If you put that in equational form, electromotive force induced is proportional to d phi by dt, but you can't write this because they're asking us to write it in words. Okay. So if you have written this, 1 mark. Not this, actually, the wordings here, 1 mark. And then Roman 2, Lenz's law. The current induced during electromagnetic induction will be induced in a way, will be induced in a way such that, it opposes the change in, it opposes the change in magnetic flux. If we induce an electromotive force, if you are trying to induce an electromotive force by increasing the magnetic flux, already existing magnetic flux, the induced current will create another magnetic field which is going to be in the opposite direction. Okay, so we have discussed that. I think we might have to use it here. Let's see. What is meant? Okay, what is meant by magnetic flux? What is magnetic flux? So they're asking for definitions. 1 mark for this one as well. Electric flux, magnetic flux, all of them have more or less similar definitions. Magnetic flux. What is magnetic flux? People, number of magnetic field lines passing through a given area. Number of magnetic field lines passing perpendicularly through a given area. Through a given area. Given area means it could be any area. It's not unit area. Careful. Given area. So there, once again, 1 mark for that as well. 1 mark. And then Roman 4. Is there another definition? Yeah. What is meant by magnetic flux density? Magnetic flux density, we know B is equal to phi over A. We have to put that into words. That is magnetic flux per unit area. Magnetic flux per unit area. Per unit area. That's it. So if you write that definition correctly, then you get 1 more mark. To which quantity the electromotive force induced in a moving conductor is directly proportional. Moving conductor. Moving conductor. Hope you can remember. There's an equation for electromotive force induced in what do you call that? A moving conductor. What is the equation? To which quantities? It should have been a plural one. No? So we know Roman 5 electromotive force induced in a moving conductor is given by BLV. Correct? BLV. So the 3 factors. One, B is going to be magnetic flux density. Magnetic flux density. It actually depends on 4 things, people. Yeah, it actually depends on 4 things. But never mind. Okay. L is length of the conductor. Length of the conductor. And the last one, speed of the conductor. V. Speed of the conductor. And there's another one. Anyone tell me? Speed of the conductor, and it should be BLV sine theta. We put sine theta also. Theta, the angle conductor creates with the magnetic field. The angle created by conductor with magnetic field. No. The angle of what? Wait. Angle. Yeah, angle created by conductor with magnetic field. This is an MCQ. This is an MCQ, no? Past paper MCQ. So we can consider all these things. Magnetic field. So let's go with half for each. Half mark for each. Half. All right. Then this part, can anyone remember how many of you have learned about this word eddy current? Can I see raise of hands if you have heard of the term eddy current? Yeah. EDDY, eddy. Okay, Shada can, of course, Shada can has come across that. Hasina has studied. Okay, good. What about the others? Nuha Azhar also can have studied. Has studied. Good. Now, eddy current people. Eddy current is a type of induced current. According to Lenz's law. But it's a special type of what do you call that, current. We have, I mean, in our theory class now, 22 batch in theory class, some of you are here in the theory class who, for example, Amna, Hafsa, Hasina, Hasna, Radishna is here, yeah, Ravan is also here. We haven't done that yet. We have to study that, and we have studied transformers. We are almost at the end of magnetic field lesson. Eddy current is just now to define eddy current number 6. Eddy current is a current induced in a conductor. Current induced in a conductor. Induced in a conductor due to the change of magnetic flux. Change of magnetic flux across the conductor. So specialty about eddy current is it's always formed in loops. Eddy current is formed in small loops. Eddy current is formed in small loops. I will explain about eddy current here, how eddy current is formed with this example. Now Roman 7 state 2 applications of eddy current. Now Roman 7, I can remember one application is used in the braking system for trains. Braking system for trains. Now what happens is when there is an eddy current, a rotating disc or something will slow down people. So in trains, we use eddy current to slow down the train. Just not the brakes alone are not enough to stop the train. Train is huge. It has a very big momentum. So we need the assistance of eddy current. And what else? And we use that in vehicle speedometers. Hope you know what that is. They are also use the concept of eddy current. So these are few of the uses. Okay, right. And now we'll move on to this question. That is, copy the figure 1 in your answer sheet and draw the eddy currents in the circular disc which is rotating with angular velocity omega. This is there's a past paper question also in one of the recent years. So let me explain. See if it makes sense to you. Okay, I think I might need a larger diagram than this. So let me erase this and go for a larger diagram. All right. So this is my disk. I'm going to draw the disk a little bigger. I'm going to be a little generous and draw it a little bigger like this. And then let's put the magnet. So you can see the magnet in the diagram. Please refer to your diagram. In that diagram, north was on top, right, people? North was on top. North is on top like this. And south here down. So I'm going to use in lines for the magnetic field. We know north to south people, we will have magnetic field lines like no problem. So those field lines will be going through the disk. This I think it would have been better if I had drawn it in 3, but never mind. But the interesting part is when you go to the corners, they bend like this, don't they? Like this. Magnetic field lines, they bend like this. Correct. So that is an important part. And here also they bend. There are some of you who might have not even heard of eddy current. You know electromagnetic induction, Lenz. So using Lenz's law, we can write that. And omega, people, how was omega? Correct me if I'm wrong. Was it rotated like this? Counterclockwise? The other way around. Someone confirm this, please. This way or the other way around? Please confirm it. Hello? Was it this way or the way around, people? This way. Okay, thank you. Right, this way. Now on this side, listen to me carefully. Inside between the magnetic poles, we have strong magnetic field. Inside, strong magnetic field, because why is a strong magnetic field? Because you can sorry, I have taken up so much of space here. Shouldn't have done that. We have strong magnetic field inside. Why do I say that? Because the magnetic field lines are closer to each other. So strong magnetic field, and outside we have weak magnetic field. I just put MF to say magnetic field. Weak magnetic field. Here also, as you move outside of the magnet, you have a weak magnetic field. So here you are entering. Now when you come from here, from where to where are you entering? Entering from weak magnetic field to strong magnetic field. Understood? Entering from weak magnetic field to strong magnetic field. So if you are entering from that is downwards. In other words, okay, wait. Entering from weak magnetic field to strong magnetic field. In other words, we can say B increasing how? Downwards, correct? B increasing downwards. Hope you can agree with me on this. When I move from now, let's say this is a part of a this part of the disk, it's entering. So it's entering from a weak magnetic field to strong magnetic field. Weak magnetic field to strong magnetic field. That means downwards. Downwards it's weak, and then as you go inside, it increases downwards. So strong, weak, strong. So downwards magnetic B is increasing. If B increases downwards according to Lenz's law, how should the magnetic field be created to oppose that? We should create a magnetic field in the opposite direction. We should create a magnetic field in the opposite direction. Correct? That is what Lenz's law means. Now you are entering from a weak region to strong region. So as you move slowly, there's a magnetic field downwards. It is weak, strong means downwards magnetic field is increasing. So as you move inside like this, if you if B is increasing downwards according to Lenz's law, a B must be induced how? In the opposite direction. This is the induced B. So if you want to induce a B like that, what kind of current we need? We need, according to right hand rule, what kind of current do we need, people? Tell me, what kind of current do we need? What kind of current do we need if you want, according to the right hand corkscrew rule? What kind of current do we need? We will need a current how? Counterclockwise. Huh? We need a current counterclockwise current like this. This is how the eddy current is going to be formed in this region. Eddy current will be formed like in loops like this. So yeah, and how? I want this thing down upwards, so eddy currents must be marked this way. They're asking us to mark the eddy currents, so we have to mark them like this. I think now you can try the same thing in this region and see if it works. Whatever I explained all this time, see if it works for the other region. This is a past paper question. It's past paper question similar to this, I can remember. It's going to be like this, counterclockwise. Now take this region. If you are moving from here to here, now from here I'm moving out now. Tell me about this. From where to where am I moving now? When this point comes out of the region, can say leaving a strong magnetic field towards a weak magnetic field. Do you agree with me? Because when you are inside, when you are between the poles, when you are between the poles, strong, and when you go out, it's weak now. So in other words, when I move from here to here, magnetic flux density is decreasing downwards. Magnetic flux density is decreasing downwards. So if you have done Lenz's law, wait, I think I forgot to add that part here. B decreasing downward means, so B induced, sorry, here B is increasing downwards. So B should be induced, another B should be induced according to Lenz's law in the opposite direction. Another B should be induced in the opposite direction, and then that is what Lenz's law means. If the already existing field is increasing downwards, we should create a magnetic field in the opposite direction to oppose that. Now already existing magnetic field, when I come out of this because the disk is rotating like this, is decreasing downwards. So what should be the induced magnetic field? What is the direction? Induced magnetic field should be what direction? In the same direction. Induced magnetic field should be in the same direction. So if I want an induced magnetic field downwards, then what should be the current? What should be eddy current? I mean, what should be the direction of eddy current? Direction of eddy current to be, use the true rule, it's going to be clockwise. It's going to be clockwise. That is how eddy current. So eddy current is not anything new if you know how to handle Lenz's law. The only problem is carefully decide, carefully figure out in direction what magnetic flux density, it's increasing, and what's the direction. You have to figure out the magnetic flux density is increasing or decreasing, and you have to figure out the direction carefully. Right? So it should be clockwise here. I don't know whether it's clear. I hope it's clear. These are the two cells you have to draw. Here counterclockwise, here it will be clockwise, and I have the reason why. I have explained you the reason. Yep. So half mark each. Half mark each for figuring it out. All right. People who knew eddy current, did you give it a try? I don't know whether you give it a try. This is how it works. Okay. Good. I will show you that past paper, and let's try that also, so that you can double check you have understood or not. Last part, Roman 8. Copy the figure 2. This is figure 2, I believe. In your answer sheet, mark the direction of the rectangular conductor PQRS, where the magnetic flux of the conductor increases with time. So Roman 8. What can I say? Already existing magnetic field. Lenz's law. Already existing magnetic field increases into the plane. So according to Lenz's law, what should happen? What should happen to it? How should be magnetic field induced? According to Lenz's law. So according to Lenz's law, a magnetic field should be induced to oppose that. How can you oppose a magnetic field increasing into the plane? How can you oppose a magnetic field increasing into the plane? So induced magnetic field should be how? So induced magnetic field must be what direction, people? Okay, let's see one answer. Yes, it should be out of plane. It should be induced in the opposite direction. This way. So if I want, this is the already existing magnetic field, and the induced magnetic field should be like this. Means if I want a magnetic field like that, what should be the direction of the current according to right hand corkscrew rule? Counterclockwise. Induced current. Counterclockwise. So this is all you have to mark. I have explained that to you with the Lenz's law explanation. This is how it should be. If it is increases in a particular direction, our induced magnetic field should be in the opposite direction. So it should be counterclockwise. Answer 2. Sorry, 1 mark. 1 mark. That is the answer for Roman 8. Okay, so overall we have 1, 2, 3, 4, 5, 6, 7, 8 points. We have used up 8 points. Yeah, we have used up 8 points. That's it. Okay. Okay, here's the question. This is from year 2017, 49th MCQ, and this is the question I was talking about. This is from eddy current. So I'm preparing another diagram, a separate diagram for me to analyze this, just like we analyzed earlier. You can take, until I prepare the diagram, you can take your time and you see whether you can figure out the answer. So this is the South Pole, North Pole, South Pole, North Pole, right? Okay. And right, I'll start explaining then. Now, you also can give it a try. So we are running out of time. So, like I said earlier, this is how the magnetic field is going to be. But as you move away, as you move slightly out of the magnet, the magnetic field is going to get weaker. Correct? The magnetic field is going to get weaker like this. It's going to get weaker as you go out like this. Like this. See? This time you have to be a little careful. Look at the way it is rotating. Now it's rotating clockwise. It is rotating. Let's focus on this region. Now here, sorry. Here we have weak magnetic field, right? Weak magnetic field. Here also we have weak magnetic field, and in the middle we have the strong magnetic field. Because as you can see, between the poles, it will be strong. Amna got an answer. Good. Let's see, Amna. Now here, sorry, you're gonna move like this. So you can say entering a strong magnetic field, weak magnetic field. Entering a strong magnetic field, this is strong, and from weak you are entering. So what is happening to B? B is increasing downwards. North is up now still. B is increasing downwards. B increasing downwards. B is increasing downwards from here. So if B is increasing downwards, then how are the induced B people? If B is increasing downwards, so B induced increasing downwards, right? Yeah, B induced must be, it should be induced upwards. Here in this region, it should be induced upwards. So I'll mark that here. B induced should be upwards like this. So if the induced magnetic field is upwards, what should be the direction of current? Now they have eddy current like this. We should draw it this way. The earlier one I draw, it's not perfect because the lines can't intersect each other. The current can't intersect each other. So I've given it this way. Now, if you want, current in upward direction, people, should be the direction of current for magnetic flux to be like the direction of current. Feel like that. It should be according to right hand rule, counterclockwise. This counterclockwise. Then on it use Fleming's right hand beside the current, direction of current. Huh? Okay, no? Induced current will be like this. Here now, if you take this region, this what's happening? Leaving a strong magnetic field. You are inside a strong magnetic field, leaving a strong magnetic field towards weak magnetic field. So when you are here, you are in strong magnetic field. When you go out, you are going to a weak magnetic field. So what can I say? B is decreasing downwards. Oh, I think I made a mistake here. It should be increasing up downwards. Sorry. Should be increasing downwards here. Sorry. It should be increasing downwards. Be increasing downwards. So here I should say be decreasing downwards. Sorry. Downwards. If B is decreasing downwards, then what about induced B? So B must be induced in the same direction. B must be in the same direction. So induced one will be like this, downwards. Here. Then people, okay, now if you want magnetic field to be down like that, if you use right hand rule, you'll be able to find out the answer. That is going to be downwards. Can I clockwise? It should be clockwise, no? It should be clockwise like this. So this is how you deal with eddy current questions. Okay. So I hope you got an understanding. Don't worry, we will be covering this again in the theory class. The answer. First one is the answer. Very good. So in theory class, let's change the terminals and let's change the direction of rotation and all those things and discuss. All right. Right. So this question is about Faraday's. Yeah, of course. PQRS is formed with a thin metal wires. The point X and Y, where X and Y are connected with the same kind of wire. Okay. PXYS is a square of side 2 meters. XQ 1 meter. YR is 1 YR is 1 meter. Okay. It is placed in a uniformly increasing magnetic field at a rate of 1 Tesla per second. So you can see they have given us the magnetic field. I will do something. I will make the magnetic field look a little, vague, so that we can mark everything clearly here itself and do the question. So give me a second until I make them a little more, light. Otherwise, it will be difficult for us to mark everything, because at the end of the day, all we need is to know the direction of magnetic field. Way too many crosses. Now it's in gray color. No, okay, no. You can see into the plane, and we have to be a little careful. We have to consider all these sides as resistors, because they have told if a unit length of the wire has a resistance of 1 ohm per meter, 1 ohm per meter, that means we have a resistance. We can mark the resistance of every wire. Now this wire, if you take this particular wire, it is 2 meter in length, so this has a resistance of 2 ohm, correct? This has a resistance of 2 ohm. And if you take this wire, it also has a resistance of 2 ohm. This wire has a resistance of 1 ohm. This wire has a resistance of 1 ohm. This wire has this has a resistance of 2 ohm, no? 2 ohm, and this one has a resistance of 1 ohm. This one has a resistance of 2 ohm, right? 2 ohm. 2 ohm, and this one also has a resistance of 2 ohm. So we have to consider this, like everything. It's better if you draw a new diagram with all these values, and this is important. Increasing magnetic field at a rate of 1 Tesla per second into the plane, that is dB over dt. dB over dt is 1 Tesla per second into the plane. Okay, increasing into the plane, increasing in this direction. Fine. Now what is the question? There we are supposed to find out the current, calculate the current through Px, Qx and xy. So when you have now I'm going to apply Lenz's law. According to Lenz's law, according to Lenz's law, okay, if already existing B, we'll write it that way. If already existing B increases into the plane, then how should be the induced EMF be induced? Induced B should be, out people, outwards, out of the plane. Okay, so I'll use the color orange. We will go with the orange color for that. So we have to say induced EMF, induced magnetic flux density out like this. So if I use the right hand rule, induced current has to be in this direction. Induced current has to be in this direction. Therefore, to have a current in that direction, there are two loops. In each loop, there will be a temporary magnetic field induced, and there will be a magnetic field induced here in this direction, because then on it will be counterclockwise, and here for it to be counterclockwise it should be like this. Okay, so I'll take this as E1, I'll take this as E2. Wait, I'll explain what this E1 E2 are. It comes from Faraday plus Lenz law. E1 induced EMF, E2 the direction. How did I mark the direction? Based on this E1 and E2 both clockwise. E1, what is E1? I have marked E1. E1 is EMF induced in PX SY, PX YS, and E2, that is EMF induced in what? XQ or Y, XQ or Y. So now we have, it's like two batteries are there in the on either corners, right? This is common for both, so we don't put a battery here. If you put a battery here, then now if I try to put a battery here, to which loop I'm gonna consider that battery? It's common for both, no? So for this loop we put it on the left side, for this small loop we put it on the right side, and we avoid the one in the middle because the middle line is common for both the loops. If you put a battery there, it will be confusing. That's why we have not put a battery there. All right, fine. Now what is the equation for induced EMF according to Faraday's law, people? We all know induced EMF according to Faraday's law is given by d phi over dt, which can be written as dBA. So that can be written as A dot dB over dt. Correct, people? A dot dB over dt. So tell me, what is the equation for E1 then? E1 is equal to, area is how much? 2 into 2, no? This area, 2 into 2 into the magnetic flux density, rate of change of magnetic flux density is 1, so that is 4. 2 into 2 is the area into 1 Tesla per second, answer is 4 volt. And what is E2 then? Anyone? What is E2? E2 is going to be equal to 2 into 1 is the area multiplied by 1 is the rate of change of magnetic flux density, that is going to be 2 volt. That is going to be 2 volt. So now I have my EMF and I have my resistors. E1 is 4 volt, E2 is 2 volt. I have my resistors and I have my battery, EMF. So let's get started. Let's mark the currents here. Current. There'll be a current here. The currents we have to find out PX, okay, QX, XY. QX, XY. All right. So a large, this is larger. So I'll take this current as I1, right? I1. Current through PX is I1. Okay, current through PX is I1, and then I1 will flow like this. I1 will flow like this, and I1 will split. There will be a current through this XY. So we'll take that current as wait. I'll put this as I2. Okay, and I don't want to introduce another current necessarily. What will be this one? Tell me quickly. So why say current will flow through this one I2 here. Okay, that is QX is I2. What is the current through XY, people? Hurry up. What's XY? According to Kirchhoff's law, it is going to be with I1 minus I2. I1 minus I2 here. It's better to reduce the unknowns, I1 minus I2. So it's better, we have only two unknowns, and all we need to do is just apply the equation and get the answer. Okay, right, now we are going to apply Kirchhoff's law, right? Kirchhoff's law. So let's first of all choose the large loop. I'm going to use loop SYXPS loop, and I'm going to apply the equation counterclockwise. Sigma E equals sigma IR. Counterclockwise sigma is 4 volt. Sigma IR, people, we have to be very careful. The current I1 is flowing through 2, 2, 2. So it is like 2I1 plus 2I1 plus 2I1. I1 minus I2 is also going through 2. So 2 times I1 minus I2. That is 4 equals 2I1, 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 another 2I1, 8I1 minus 2I2, and you divide everything by 2, you'll be getting 2 equals 4I1 minus I2. First equation. All right, fine. We have two unknowns, therefore we will need another equation. For a change, let's apply the equation for this part. For this one, that loop is QXYRQ. QXYRQ. And for that loop also I'm going to apply it clockwise, so counterclockwise. Sigma E equals sigma IR. Right, what is sigma E here? Just 2 volt. Sigma IR, I2 is flowing through 1, 2, 1. So that is 1 into I2, 1 into I2 plus, and this part of I2 is counterclockwise. 2 into I2, again 1 into I2. Now we have to be careful. This one is not counterclockwise. It is clockwise, this current. So you have to put a minus here and say I1 minus I2, current is flowing to. Do you hope you all understood how this minus came? I'm applying the equation in the anti-clockwise direction. This current, this current, and this current, they are in counterclockwise direction, but this is in the opposite direction. That's why this minus. So 2 equals I2, 2I2, I2, 4I2, 4I2 here. Here minus I1 into 2 is minus 2I1. Minus into minus becomes plus, plus 2I2. Therefore, that is 6I2 minus 2I1. Therefore, finally, the equation is when you divide everything by 2, it's 1 equals 3I2 minus I1. 3I2 minus I1. Alright, people. Second equation. If you wish, you could have applied it for the outermost circuit as well. Up to you. At the end of the day, you will get equations like this. Then what do you think we can do? We have to find I1 and I2. So wait. Let's multiply the first one by 3. Okay, let's multiply the first one by 3. We must multiply the first one by 3. I multiply the first one by 3 on the left hand side. I'm going to get 6 equals to 6 equals to, on the right hand side I'm going to get 12I1 plus 3I2, right, plus 3I2, third equation. Then I'll add 1 and 3, sorry, I'll add 1 and 3. When I add 1 and 3 on the left hand side, what am I getting? The left hand side I'm going to get what, people? 2 plus 6, isn't it? 2 plus 6. 2 plus 6 the no, wait, what I'm saying, I have to add 2 and 3, no? I have to add 2 and 3, sorry. I have to add 2 and 3. I have to add 2 and 3. Then on here, 3I2 and I2 will get cancelled. Wait, what am I saying, people? Okay, this is the problem. I have forgot this minus. Apologies. There's a minus here. Huh? There's a minus in the first equation, people. Right. I multiply the first equation by 3. So 6 equal to 12I1 minus 3I2. Sorry. Let's add 2 and 3. When you add 2 and 3, we will be getting 1 plus 6 is 7 equal to 3I2 and minus 3I2 will get cancelled out. Minus I1 plus 12I1. When you add them, it will be 11I1. 11I1. So I1 is actually equal to 7 over 11 ampere. 7 over 11 ampere. Supernova 11 is 0.64 ampere. I1. Then what is I2, people? I1 we know. Let's apply that equation for in the second one. 1 equal 3I2 minus 7 over 11. So I2 is going to be equal to, this goes the other side, becomes 18. Wait. Then I can write it this way. When I take this to the other side, it will be 18 over 11 equal to 3I2. So what is I2? So I2 is going to be equal to, when you divide 18 by 3, it's 6 over 11 ampere. What is 6 over 11? 5.45 ampere. 0.54 ampere. That is I2. All right. And what are we supposed to find out next? So we have I1 is the current through Px, I2 is the current through Qx, and finally the current through Xy. Current through Xy will be, so let's write the final answers. I1 is in fact who? Current through Px. Current through Px. And I2, this is current through I2 Qx. The last one, current through xy. What is current through xy, people? Current through xy we have already found out, that's I1 minus I2. I1 minus I2 is 0.64 minus 0.54. I'm roughly getting 0.10 ampere. Kirchhoff's law. But to start that, you need Lenz's law and Faraday's law. Good. So marking scheme right, marking scheme. You have to put 1 mark for this diagram, marking all these resistance and everything and preparing that, and half mark each for figuring these two out. Half mark for this, half mark for this, and then Kirchhoff's law. So when you apply Kirchhoff's law, we need to get 2 equations, people. So 1 mark for this equation and 1 mark for this equation. You might have got another, I don't know, you might have not exactly got the same equation, but at the end of the day this, and then the final answers, half for each, half for this one, half for this one, and half for this one. Total of 15. 1 2 3. Yeah, I think they are saying half, bonus half, but never mind. Okay. We'll give half for this one right now. Okay, I think. Check, will you? Anyone who tried this one, raise your hands. Anyone who gave this an attempt? This question. It's a really good one, people. A very different type of question where they have considered all the types of laws in one question. Okay, so it's definitely worth the try. If you couldn't get the answer, have an idea now, please try from the scratch again. Okay, see, we have applied Lenz's law, found the E, and then put here, and then Kirchhoff's law. The middle part you have to leave it blank. Like I said, why haven't I marked a battery in XY? XY is a side or the part of the circuit which belongs to both the loops, small loop and the large loop. So if I put a battery there, that there'll be a confusion to as to which side it depends, to which side it belongs, nah? Right. So we're going to try the first of fourth question, part A of fourth question, because part B is quite similar to a question we did before today. There's no point of repeating the same thing. Particle carrying charge Q enters perpendicularly to a uniform electric field of field intensity E with velocity as shown in the diagram. Okay. A magnetic field of flux density is created from the moving charge perpendicular to its direction of motion. So you can see they have already given you E and B. They've already given you E and B, unlike the previous question. Write an expression for the force Fe created on the charged particle by electric field. So that is very simple. Fe, that is equal to what, people? Charge is given. Have they given the charge? What is charge? Plus Q, yeah, QE. Done. Okay. Write an expression for the magnetic force up. That is also simple. Fb, that is equal to BQV. QV. And Roman 3, clearly mark the forces acting on the moving charge Q. So directions are important. Now whenever they have given you a electric field, we need to know where the positive plate and the negative plates are. So positive plate is definitely going to be on top. I mean, from positive to negative, na people, the electric field intensity is going to be directed. On top we have the positively charged plate, at the bottom we have the negatively charged plate, and since it's a positive charge, in a positively charged particle, it will be attracted towards the negative plate. So the electrostatic force will be acting vertically downwards, just like the previous question, nothing new. It will be acting vertically downwards because it is going to be attracted towards the negative plate, since it's a positive charge, remember. What's the direction of magnetic force, people? What's the direction of magnetic force? Again, Fleming's left-hand rule. This one is attempting to move towards right side. Therefore, we have to, the current is going to be in the same direction. This is the direction of current. So if I apply Fleming's left-hand rule, magnetic field is into the plane. Sorry, forgot to mark that. Magnetic field is into the plane. So index finger will be pointed into the plane. Middle finger will be pointed towards right, and I'm getting it upwards. Upwards. This is the direction of magnetic force, Fp. Up. They have given it as Fb, yeah. So we have to go with Fp. This is the magnetic force. Upwards. Fleming's left-hand rule. I'm not going to repeat it. Okay, never mind. You know what? Let's just draw it for this. Into the plane is our index finger. The middle finger will be pointed towards left. If you point all your fingers that way, thumb will be pointed upwards. And that's how we are getting the direction of magnetic field. Right then, Roman 4. Clearly draw the paths of the charge when Fe is bigger than Fb, Fe is smaller than Fb, Fe and Fb are equal to each other. Very simple. That first part. When your Fe is bigger than Fb, what can I say? There's a resultant force. There's a resultant force in which direction? Downwards. Therefore, the particle, it's going to take a path like this. Because the particle is attempting to move towards right at the beginning, it's pulled downwards, therefore it will do this. And the second scenario, the opposite of that. When Fb is bigger, that is the magnetic force is bigger, then we have a resultant force where? Upwards. We have a resultant force upwards. Therefore, the particle which is attempting to move towards right, it tends to bend upwards. And finally, what will happen in the last one, people? Hurry up. When you equate Fe and Fb, zero resultant force vertically. People tell me then what will happen? The particle will continue to move straight. Particle will continue to move straight without a change in direction. I think this part was not really there in the previous question. These things we already discussed, but anyways, yeah. I think this will be enough for this question, guys, because the previous we discussed the same thing in the previous question too. Because symbols are B not Q, E everything V. So I don't think